Okay, thank you, Mike. And so thankfully today I don't need to draw any hexagons or honeycomb lattices, so the whole thing will be on the board. And so I'm going to discuss today a set of ideas that has emerged motivated by the flat bands realized in moiré systems like twisted bilayer graphene that enables us to kind of understand more deeply the structure of these topological flat churn bands and how they are related to lambda levels. And it also allows us to make some sharp statements about their interaction physics. So most of these ideas actually grew out of a very interesting model called the chiral model proposed in this paper. And to understand this model, let me briefly write the Hamiltonian for the Bisters-McDonald Hamiltonian that we wrote last time, which have the following form. So this is a 2 by 2 matrix in the layer space. And each of these is a 2 by 2 matrix in sublattice. And it has the following form. I didn't write it very explicitly yesterday, but it looks like this. So W0 and W1 are some simple functions of R. Their form is not important. But the important thing about this Hamiltonian is that it depends on two parameters. Sorry, U0 and U1 are functions of R that are simple. And the Hamiltonian depends on these two parameters, W0 and W1. And as we discussed last time, W0, because it sits on the diagonal of this matrix. It corresponds to tunneling between sublattices, between the same sublattice, so A to A or B to B, while W1 corresponds to tunneling between opposite sublattices, so A to B or B to A. And we discussed that in the in the realistic model when we have lattice relaxation. There is a slight preference for AB over AA because of some energetic reasons. So W0 tends to be slightly smaller than W1. So W0 divided by W1 is usually between 0.5 to 0.8. These all are estimates from some ab initio calculations. Now, the chiral model is obtained by taking the limit where W0, so the smaller of the two, is just set to 0. And the reason this gives us something interesting is that in this limit, the Hamiltonian has an extra symmetry because once we set W0 to 0, so we are kind of kicking out these terms on the diagonal. So the T of R becomes completely off diagonal in sublattice space. So this is really AB sublattice space. However, the kinetic term is also off diagonal because it has sigma. It's written just in terms of sigma x and sigma y, which means that the full Hamiltonian is off diagonal in sublattice. Another way to say it is that the Hamiltonian anti-commutes with the sigma z operator. And such kind of symmetries are usually chiral symmetries. And the reason is because we can actually write this Hamiltonian in the form of a chiral Dirac Hamiltonian that has zeros on the diagonal and some operator and its dagger on the off diagonal. Now, it turns out that this Hamiltonian has a lot of interesting properties, and in particular, it has a perfectly flat bands, so at a set of magic angles. So we can use this Hamiltonian to actually understand this phenomenon, the emergence of magic angles in the Bisters-McDonald model. And let me just, to set the notation, and to make everything simpler, I'll work in some dimensionless units. So I'll be measuring the energies. By the way, is this font big enough for those at the back? Okay, I'll make it bigger. Okay, I'll make it bigger. So energy. So the energy will be measured in units of h bar Vf. So this is just the natural energy scale at an angle theta. I'll measure the length in units of which is the moiré length scale. And once I do this, this model only depends on one dimensionless parameter, which was called alpha. And this is the ratio of this tunneling W1 and Vf kd theta. So alpha is a dimensionless coupling that depends inversely on the angle. And in terms of this, I can write the, I can write this operator D. Oh, yeah. As follows, where M is just some 2 by 2 matrix that depends on space. Its form doesn't concern us. And alpha is this dimensionless parameter. And here I define the complexified variables. Z is x plus iy. And this derivative is the derivative relative to z bar, which is 1/2 dx plus I dy. So the first the first consequence of the chiral symmetry is that if we have any zero mode of this Hamiltonian, then it will be an eigenstate of sigma z. So if I have d psi equals to 0, I can choose psi such that acting with sigma z gives me plus or minus 1. And since this is the AB space, this means that zero modes will have the form, will have one of these two forms. So they would be completely sublattice polarized. Now we do have, we know that this Hamiltonian has some zero modes because if you remember, we started this Hamiltonian from a Dirac dispersion at these points, which we called k plus and k minus. And actually, these points are guaranteed by C3 symmetry. These Dirac points are stable because of, actually, they're stable because of C2T symmetry. But this sigma z symmetry also guarantees that they would be pinned at zero energy. And C3 symmetry guarantees that they cannot move. So we know that we always have a zero mode at these 2 points. And let me, for the moment, focus on one of the points, like k plus. So what this tells me is that at the point k plus, I actually have 2 zero modes. One of them localized on sublattice A, and the other localized on sublattice B. So the one localized on sublattice A will look like this. We'll have this form, which means it's a zero mode of the D operator. So D at k plus is equal to 0. The one localized the sublattice B will be a zero mode of the other operator, of the dagger. And the two zero modes are related to each other by C2T symmetry because C2T symmetry acts within the valley and flips sublattice. So they're related to each other by some complex conjugation and flipping R to minus R. Now let me focus on sublattice A, on this zero mode. And for simplicity, I will choose the momenta such that k plus is the origin of my momentum. So this is my 0 point. This will make things simple later. So one observation about the Hamiltonian is that this D operator only contains the anti-holomorphic derivative, the derivative relative to Z bar, but not the derivative relative to Z. So it's tempting to say the following, which is that if I have a zero mode, psi 0 of R, and now I'm really focusing on sublattice A, I can form another zero mode or another family of zero modes, F Z psi of R, where Fz is some holomorphic function. And if I can form this family of zero modes, maybe maybe this family will give me actually the full flat band. And that's what usually happens, for example, in the Landau levels. So in the Landau levels, you can start from one state in the Landau level and multiply by some holomorphic function. At the lowest Landau level, multiply by some holomorphic function and generate the full Landau level. However, here we encounter a problem, which is that a holomorphic function either blows up at infinity or has to be a constant. So that's called Liouville's theorem. So bounded holomorphic function has to be a constant. So this doesn't help us much. If we multiply a wave function by a constant, we get the same wave function. So what can we do next? So I mean, given that we kind of know numerically that this model has some perfectly flat bands. So the next thing we can try is to take the Fz to be a meromorphic function, which means it's a function that has some poles, but it actually has some non-trivial structure, and it is periodic over the unit cell. So if we find the meromorphic function that has the following property, so Fk of Z plus R, where R is a lattice vector, is equal to e power I k dot R Fk of Z, then given one zero mode that describes the Bloch state at momentum 0, multiplying it by this factor gives us a zero mode that has momentum k, because under translation, this combined object will behave like a Bloch state with momentum k under translation. Of course, the problem is a meromorphic function has poles, which means that generally this object is not normalizable. So it's not a valid state, unless the wave function itself has a zero that I can cancel against this pole. So the main argument in this Tarnopolsky et al. Paper is that the existence of a flat band in this model is equivalent to having this wave function, which is the zero energy, which is the wave function at zero energy of the Dirac point, that it has a zero in real space, somewhere in real space. And if it has a zero in real space, we can construct a meromorphic function where the pole is exactly at that point and the zero and the pole cancel, and we get something normalizable. Now, this is a huge simplification, because naively getting a flat band requires tuning an infinite number of parameters, while here we just need to tune 4 parameters, because we just have a spinor, and actually not only 4, because this is now a sublattice polarized wave function. So I just have 2 non-vanishing components, and we need these 2 components to vanish at once. Furthermore, what they showed in this paper is that there is a special point in real space, which is corresponds actually to the AB stacking position, where a combination of C3 symmetry and some other symmetries implies that one of the 2 non-vanishing components of this has to be 0 at that point. which means that at that point, this wave function has only one generically non-vanishing component. So we have one real parameter that we need to tune to get a completely flat band. So instead, we have reduced the problem of getting a flat band from tuning an infinite number of parameters to tuning just one parameter. And since our theory already has one real parameter to tune, which is alpha, this tells us that as we change alpha, we generically expect, not necessarily, but we generally would expect that we'll be able to hit zeros and get a set of flat bands. And that's precisely what happens in this model. So if we look at the absolute value of this psi 0 at this special point RAB, like not the absolute value, the full value, we see that it goes through a sequence of zeros as I change alpha. And this would correspond to the total bandwidth of the band going through, actually, it goes down as a function of alpha. And so the sequence of magic angles, you can just find them by numerically solving this Dirac equation, this equation at the Dirac point with the particular potential, and get a certain sequence. So for example, the first magic angle is around 0.586. Second magic angle is 2.21. Third is 3.75, etc. And this, remember that alpha is inversely proportional to the angle. So actually, higher alpha means smaller magic angle. And the smallest alpha corresponds to the largest magic angle, which is around 1 degree. So this is the magic angle we discussed in the last lecture, and this is where kind of most of the of the experimental work has been, because at these higher alphas, these are angles that are too small, that the effects of lattice relaxation are very strong, that this whole description kind of breaks down. I also want to mention that the overall behavior of the model is more or less universal. It only depends on the symmetry, but the value of these magic angles depends on the details of these potentials. So for example, if I go beyond the leading harmonic and add kind of further harmonics to the potential, I'll get the magic angles at different places. But the phenomenon of magic angles is kind of a robust general feature of this kind of model. Now, I haven't really explained to you how do we construct these functions. So let me do this now. So in the original paper, these functions were constructed using something called Jacobi theta functions. But many of the expressions are much simpler if you use a related elliptic function called the Weierstrass sigma function. And I will not really write the explicit expression. It has there's some expression for this Weierstrass sigma function. I'll just write its properties. So the Weierstrass sigma function depends on, so it takes a complex argument, and then it takes two complexified vectors that correspond to lattice parameters. So we think of these A1 and A2 as the basis vectors of the lattice. And it has the properties that it is an odd function of Z. Which means it has a zero first order at Z equals 0. And the second most important property is how it behaves under translation by a lattice vector. So here R is n A1 plus m A2. Let me move it up a little bit. Now I've made the following, I'll be throughout using the following convention, which is assuming that the area enclosed in the unit cell is 2 pi. So A1 cross A2, this defines a certain length scale, which I call LB squared in analogy to the Landau level problem, and I'll always take LB equals 1. So in this case, I have this simple transformation properties of the sigma function under translation, where this eta of r is just, it's a factor defined for convenience. So eta of r is equal to +1 if r over 2 is a lattice vector, and -1 otherwise. So if I now use this property, it's relatively easy to verify that if I define fk of z to be sigma z plus ik, and from now on I will not write the lattice parameters explicitly because I'm always assume I have some lattice, so it's the lattice of the twisted bilayer graphene system. E power I half k bar z divided by sigma z. So if you substitute this rule for translation under for any lattice translation in this expression, you'll see that it satisfies this relation. So what this tells me is that this argument not only predicts that this model has some perfectly flat bands at a certain set of magic angles, it gives me the flat band wave functions, because it tells me that the flat band wave functions at a general k is equal to this f k of z times psi of 0, which is, yeah, let me write it explicitly. This form of the wave function is very interesting. And for those of you who have been working with Landau levels, it should immediately suggest something that looks very similar to the wave functions in the lowest Landau level. Because the wave functions in the lowest Landau level, irrespective of the gauge you choose and the kind of the geometry you look at, they always have the form of some holomorphic function or some function that depends. Actually, let me. I can put sigma z here. Now this factor is not singular, and this factor is holomorphic. So this form of the wave function tells me that the wave function has the form of a holomorphic factor, where the quantum number labeling the different states within the band, where the dependence on these quantum numbers enters, times a common factor, which is common to all the bands, to all the states in the band. It doesn't depend on k. So this looks exactly like the wave functions in the lowest Landau level. For example, in the standard symmetric gauge on the disk, the wave functions in the lowest Landau level look like Zn e power -1/4 z bar. And this part is not holomorphic, but it's common to all the states, while the part that depends on n is purely holomorphic. In fact, there's there's a much closer relation of these wave functions to the wave functions of the lowest Landau level, which you can see by as follows. So let me, for this, I'll need to slightly review something about the Landau level physics. So you're maybe used to solving the Landau level wave functions in the disk geometry if you do the symmetric gauge, or in the rectangular geometry if you do the Landau gauge. But if you solve the the problem with Landau levels on the torus, you can actually choose the wave functions, the basis of the Landau levels, to be eigenstates of the magnetic translation. So we know that in the Landau level, we don't have regular translations because of the strange way the spatial position enters the magnetic vector potential. So even if the magnetic field is completely uniform, so the system is supposed to be translation symmetric, the naive translation operator doesn't really commute with the Hamiltonian, and instead we need to combine the translation operator with some gauge transformation. And when we do this, we get something called a magnetic translation operator. And the main feature of this magnetic translation operator is that the magnetic translation operator corresponding to two different vectors don't commute. Instead, they satisfy the magnetic algebra, which is I U wedge V. And by U wedge V, I mean, so U and V are 2D vectors, and I mean basically taking their cross product and taking the Z component. So it's like Ux Vy minus Uy Vx. And of course, I'm here assuming the magnetic length is equal to 1. So this tells me that magnetic translations generally don't commute. But if I take two vectors that enclose an area that's a multiple of 2 pi, they would commute. So if I take basis vectors A1 and A2, such that A1 cross A2 is plus or minus 2 pi, and construct the lattice vectors R n plus MA2, then for any pair of lattice vectors R1 and R2, or R and R prime, these magnetic translations commute. And actually, yeah, go to the front. So as a consequence, I can actually find a common set of eigenstates of all lattice magnetic translation, because they all commute with each other. And these set of eigenstates will look like basically Bloch states. So they will look like this, where it's customary to define them with this factor of eta of R for convenience. So I'll call these LLL. And these wave functions can be written explicitly in terms of the sigma function. So they have the form so comparing this expression to the expression over here, we see that they share almost everything. So this the sigma function piece is common. This piece that has e power I half k bar z is common. And the difference is that we have this more complicated factor instead of this factor here. One way to see this is to just write the wave functions over there in terms of the Landau level wave functions. And I'll write it like this. Where I define this e power minus kr as basically what is left over. So it's but it's a positive real number. Doesn't have any spine or piece. So it's the norm of this vector psi of r divided by e power minus 1 over 4 zz bar times the norm of sigma z. And this is a vector that just contains the spinor part but has norm 1. So you can write it explicitly like this. So the exact expression is not important, but the important thing is that this object has norm 1. So what this tells us is the following. It tells us that the wave functions of this chiral model are given by the wave functions of the lowest Landau level, modulated by some factor that is periodic in real space, because this function, now because this has a 0 and this has a 0, they cancel. So this function is non-singular and it's periodic in real space. So it's a lowest Landau level wave function modulated by a function that's periodic in real space times a spinor, but that has norm 1. And that doesn't depend on momentum at all. This means that if I ask any question I'm interested in that doesn't care about the layer degree of freedom, I would take overlap of different wave functions at different momenta, and this part would completely drop. And I can basically think of the problem as a problem in terms of these wave functions. Now, these wave functions are the wave functions of the lowest Landau level times the periodic modulation, which actually translates to the wave functions of the lowest Landau level in a non-uniform magnetic field, of a Dirac particle in a non-uniform magnetic field. And I can relate. So I can relate the magnetic field to this object, to this factor. So I have a total magnetic field whose average value gives me a 2 pi flux per unit cell, and its variation relative to the average is just given by the Laplacian of this factor K of R. So we started from this. Yeah. Are there questions? Yeah.
These are the norm.
This is it's the norm in the spinor indices, but not the norm. It's not the norm of the in real space. So it doesn't contain any real space integral. This is evaluated every R. Yeah, it's clear. So I just had this object and I split it into its magnitude and its vector piece. Yeah. So what we have done here is that we mapped the chiral model flat band wave functions to a Dirac particle. So these are the same as a Dirac particle in non-uniform magnetic field. And this mapping ultimately comes from the fact that the chiral model the chiral model has this holomorphic structure because of the separation between holomorphic and anti-holomorphic derivatives that allows us to write the wave functions in terms of a holomorphic piece times a piece that doesn't depend on momentum. Now, it turns out that this model also has a dual holomorphic structure in momentum space. And this you can already see from the fact that if you look at this wave function, so K of R is a periodic function, because if you look at this, you'll find that, so this is periodic. This sigma z grows as a Gaussian, and this Gaussian cancels that growth. Yeah.
Periodic function.
Yeah, this would be also a periodic function.
Average to 0.
So this is a periodic function that averages to 0. So if you look at this factor, you see it's almost symmetric in terms of z and k. But there is the extra piece, which is this one, that actually is holomorphic in z and anti-holomorphic in k. However, if you look at the cell periodic functions, not the Bloch states, So the cell periodic functions are defined simply like this. You'll find that these are like this factor in the numerator becomes k z bar, and then the rest is the same. So now these cell periodic states are holomorphic in K rather than being holomorphic in Z. So another property of this model is that the cell periodic functions U of K and here this K is Kx plus IKY. And of course, I should mention that if you try to normalize these wave functions, then the norm itself will not be holomorphic in K, so you'd lose the holomorphicity. So this is a statement that it's possible to multiply U of K by a K-dependent factor to make it holomorphic. So these are all properties that appeared in this chiral model, and then there's then two natural questions to ask. The first one is, how general are these properties? Are there other models where this will occur? Second question is, if I give you a model and maybe you can compute the wave functions numerically, how do you know that they satisfy this kind of properties? And third, these properties suggest a shared structure between the chiral model wave functions and the Landau levels. Can we also expect similar interaction physics? And in the following, I'd like to kind of answer all three questions. So first, I'd like to answer the question, how general are these structures and how do we diagnose them? So the first thing to notice is that these two properties, holomorphicity in K space and the form of the wave, the fact that the wave functions, so psi of K is equal to some holomorphic function that in Z that depends on K times psi of 0, so that these two properties are actually equivalent. So if you have a model where you proved one property, you can immediately deduce the other. Now, this property can be written in a different way, which is that what this property says is that if I take a wave function from the band, I multiply it by a holomorphic function, I don't get out of the band. So it tells me that if P of K is the band projector at point K, then Z times psi of K is the same at P of K, Z times psi of K. Or if I define the kind of the dual projector, 1 minus P of K, this statement means that Q of K, Z psi of K is 0. Is this step clear, or are there questions? So I now want to show that this both implies holomorphicity and is implied by holomorphicity. So let me start first by assuming that U of K is holomorphic. So if U of K is holomorphic, it means that 0 is equal to dk bar U of K. And then I can write U of K as e power minus I k dot r psi of K. Acting with the derivative first acts here, gives me minus I half Z psi of K plus, and yeah, there is this factor equivalent. Now I can get rid of this factor, and I can act with Q of K on both sides. So the first term will give me Q of K Z psi of K. with some minus I over 2. The second term, oh, sorry. This second term actually gives me 0 because the derivative of psi of k is a linear superposition of psi of k plus epsilon and psi of k. Of course, psi of k acting on the projector outside the band, outside the space I'm interested in, gives me 0. And if I shift k because of momentum conservation, this projector acting on it also gives me 0. So this object is 0. So this tells me that so this is the first direction, going from here to here. To do the opposite direction, yeah.
E of k z times psi of k. Which the second line?
Here. Here? This row.
When you multiply psi of k by z, doesn't it go to a different momentum sector generally?
Well, you can choose the so you can generally, if you multiply, it will have some weight on that momentum sector, and the statement is that I'm saying that you'd be
to the full band.
So you're saying here shouldn't be this should be the full projector, not just the projector on the on that momentum. I think you are right. Okay, let me check it. Yeah, so that I don't want to say something. But I just wanna now say the opposite direction of this derivation, which is if I start from this, I also should deduce holomorphicity. So of course I can run back this argument, and if I start from this, I will easily deduce that q of k dk bar u of k equals to 0. But this means that u of k is proportional, that the holomorphic derivative of u of k is proportional to itself, because this q of k is just 1 minus some overlap of u of k with this object times u of k. But as I said, it's not that u of k is holomorphic in any gauge. There is a very specific gauge that's holomorphic. And what this relation tells me that I can define an alpha of k such that and I can define this object which now satisfies this. So this shows that yeah, this relation does imply that dk bar u of k is equal to 0. I can multiply uk by an appropriate factor to get to make it holomorphic. So it's not an accident that the wave functions in the chiral limit, in the chiral model, satisfy these two properties. They're actually related to each other. But there's a much more general structure here, and this general structure also allows us to detect this property of the bands, what bands satisfy these kinds of conditions very easily. And to do this, I need to define an object called the quantum geometric tensor. So the quantum geometric tensor, maybe Raquel talked about it on Tuesday, but let me introduce it here anyway. So it's defined as follows. where this D is a covariant derivative. So it's dKA minus IA, where A is a Bray curvature. Actually here defined by opposite sign than the default convention. And I can also write this in terms of this Q of K as okay. So this is just some object I can define for the bands. But there's a way to decompose this object that makes it makes its physical meaning much more transparent. So this is a Hermitian matrix, and it's positive semi-definite. You can see this from the fact that it's for any vector, this is just a norm of some vector. So I can write this T. I can decompose this complex Hermitian matrix into a real symmetric part and an anti-symmetric part, an anti-symmetric imaginary part. So the real symmetric part, so this is all K-dependent, of course. Let me make sure about the convention. Yeah. So this part is a very familiar one. This is the Berry curvature. And you can easily see from this expression when you anti-symmetrize it, you get the Berry curvature. And this part is a quantity called the quantum metric. So it's a metric that describes how two cell periodic states, how the overlap of two cell periodic states changes as the momentum difference between them grows. So notice that this is something that should be familiar, but so the psi of k, the Bloch states, are orthogonal at different momenta, but the cell periodic states are not orthogonal at different momenta. So generally, this overlap is non-zero, but it's generally less than 1, because the overlap of any two different vectors is less than 1 unless they are the same. So we can expand it to leading order like this. So what can we say about this object? So first, the fact that it's positive semi-definite means its determinant is positive. But we can write its determinant in terms of the determinant of G and of omega, because this object is simply gxx, gxy plus I half omega, gxy minus I half omega, gyy. So the determinant of T is equal to determinant of G minus 1/4 absolute value of omega squared. So this gives me immediately an inequality that I can write that relates the determinant of the metric to the Berry curvature. So it tells me that the square root of the determinant of the metric has to be larger than or equal 1/2 the absolute value of the Berry curvature. And this relation should hold for every momentum. There's another relation I can write, which is a very simple relation that holds for any 2x2 matrix. It's basically the statement that the arithmetic mean is always larger than the geometric mean. So the root of the determinant of G is the geometric mean of the eigenvalues. So this has to be smaller than or equal 1/2 the trace of G. So this sequence of inequalities always holds in 2D. And then we can ask what happens if some of these inequalities are saturated. So if the second inequality is saturated, this is something known as the determinant condition. It's a condition that people have studied in the kind of earlier work about fractional Chern insulators. And it does have some geometric interpretation that I mean, I will discuss a bit later. But a much more powerful condition happens if both of these inequalities are saturated. So if the first inequality is saturated, if I have two numbers where the arithmetic mean is equal to the geometric mean, the two numbers have to be equal. So if the two inequalities are saturated, the two eigenvalues of G have to be equal. So G has to be proportional to the identity. If this inequality is equal, given that I know that G is proportional to the identity, then the solution to this whole condition, which is called the trace condition. So this implies that G AB at K is equal to 1/2 delta AB omega K. So this condition is known as the trace condition. Now the trace condition, of course, implies that because this inequality is satisfied, implies that the quantum geometric tensor has a zero. And it's not very difficult to construct that zero because the quantum geometric tensor now has the form. And so when this condition is satisfied, and if I assume the metric is non-singular, so it's non-zero everywhere, then either G is equal to, then the Berry curvature cannot be zero, cannot vanish, and either G is equal to plus or minus the Berry curvature. So I'll take the plus sign, so for simplicity. So I'll have here 1 I minus I1, and then I can construct a zero mode omega, where omega is 1 I. Now, it will be immediately obvious using a two-line argument that the trace condition is equivalent to the conditions we've been writing over there. Is equivalent to these two conditions that we've been writing here. So we have the quantum geometric tensor is equal to 0. And from this, we can deduce that but from the definition of this D that is here, which have this Q, we will get that Q K. And here we'll have a linear superposition of dx and dy, but dx has 1 and dy has I, because that's the form of the vector. So what we will get is exactly dk bar u of k equal to 0. And that's precisely the condition that we wrote above, that led to uk being holomorphic and psi of k equal having this holomorphic structure in real space. So if we have now found kind of three different ways to characterize the same set of properties of bands. The first one is the trace condition, that the trace of the metric is equal to the Berry curvature. The advantage of this formulation is that this is a very easy thing to do numerically. So you can take any model and compute the single particle wave functions and check the trace of the metric versus the Berry curvature. Also, it gives us a quantification of how far we are from kind of this limit. So you can compute this object, which is always positive, and if this object is kind of small in specific units, you can say that this band is close to satisfying this condition. The second equivalent property is that the cell periodic wave functions are holomorphic in K. And the third equivalent property is that the wave functions all the k dependence of the wave functions is contained in a holomorphic factor. Or another way to say this is that if I multiply the wave functions of the band by any holomorphic function, I don't get out of the band. And clearly, this is a structure that is there in the lowest Landau level, and that is shared by at least the bands of chiral model of twisted bilayer graphene, but maybe many other bands that satisfy this trace condition. But I want to make some notes about this trace condition. So the first one is that, and that's maybe a technical comment, but this trace condition is equivalent to the structure of the Bloch states on the Brillouin zone has Kähler geometry, or has a Kähler structure. Okay. Kähler structure means that we have a metric structure, a symplectic structure, and a complex structure, and they're all tied together. And in particular, both the determinant condition and the trace condition imply that there is a Kähler structure. But for the determinant condition, this Kähler structure is k-dependent. So it's the matrices that define what is complex conjugation depend on where you are in the manifold. So it's a local Kähler structure, which doesn't translate easily to some clear statements about real space. But for the trace condition, we get a global Kähler structure. So that allows us to kind of make all these statements in real space. So trace condition gives us a Kähler structure. Second is, so we know the lowest Landau level, of course, satisfies this condition because the wave functions have this form. But the lowest Landau level also satisfies other conditions, and most importantly, that the Berry curvature is uniform, so doesn't depend on momentum. And it turned out that these two properties are sufficient to uniquely fix the lowest Landau level. So any band satisfying trace condition plus uniform Berry curvature is basically equivalent to lowest Landau level. Higher Landau levels satisfy the uniform Berry curvature condition, but do not satisfy the trace condition. So for the nth Landau level, trace G is equal to n plus half omega. So higher Landau levels do not satisfy the trace condition. But one curious aspect is that if I take the 0th to the nth Landau level as a group of bands together, then they still satisfy the trace condition. So 0 to n and that's something that would be very tricky to see if you just try to compute the kind of multi-band generalization of all these expressions. But it's very easy to see if you use this definition. So this definition tells me that if I multiply wave functions by z, I don't get out of the space of interest. And if I multiply up wave functions in the nth Landau level by z, I can go down in Landau levels, but I can never go up, because z acts like a partial z bar. And if I reduce the number of z bars, I go down in Landau levels, but not up. So if I take 0 to n multiplied by z, I would never get higher Landau levels than n. And so the last thing I want to discuss about the structure is, okay, so we have the structure. It seems to be kind of very nice, but what do we do with it? So of course, Landau levels, and particularly the lowest Landau level, is nice because it has all these exotic states, like the Laughlin states, the fractional quantum states, non-abelian states, and so on. So if we have the structure, can we say something about those states? So the first thing we want to answer here is, of course, the Landau level have the structure, the lowest Landau level has the structure, but has also other structure. In particular, it has this uniform Berry curvature, and it has, actually, okay, these two structures together give me this magnetic translation symmetry, which also translates to a certain algebra of the density operators called the GMP algebra. And on the face of it, you know, Landau level has a lot of nice properties, and it's not very clear which one leads to what aspect of the physics. And for some time in the field of fractional Chern insulators, which was aiming to find, to engineer band structures that would yield a something like the Laughlin state when you, if it's a flat band and you partially fill it, you fill it like at 1/3. The philosophy taken was usually to try to mimic as many aspects of the lowest Landau level as possible. So we try to make the to reproduce the GMP algebra, we try to reproduce the uniform Berry curvature, we try to reproduce this trace condition. But this philosophy doesn't really tell us kind of which one of them is important and which one of them is just an accident. But there's a hint what property of this is important. So as I said here, that all Landau levels have uniform Berry curvature, which means all Landau levels have magnetic translation symmetry, all Landau levels have the GMP algebra. But only the zeroth Landau level satisfies the trace condition. So if I look at higher Landau levels, they don't satisfy the trace condition. So this suggests that if I want quality of the band that really picks out the zeroth Landau level, this quality should have to do with the trace condition. And this argument can be made a lot sharper as follows. So one very controlled analytical argument to understand the fractional quantum Hall states, like the Laughlin state, in the lowest Landau level, uses something called pseudopotentials. So the original formulation of pseudopotentials by Haldane was for the rotationally symmetric case, and it uses the angular momentum basis. But there is a subsequent formulation by Trugman and Kevelson, which just took the perspective, and it's more convenient when we're thinking of a band, where we just take the perspective of saying, okay, I have an interaction that is short range, so I can expand it in powers of the range of the interaction, which will be an expansion in gradients of, in the powers of the Laplacian of a delta function. And I can call these coefficients Cn. So pseudopotentials are obtained by truncating this series. So for example, the first pseudopotential will be obtained by just taking the first term of this series. So the thing about pseudopotential Hamiltonians is that they are non-trivial Hamiltonian. So they are not, for example, commuting projector Hamiltonian, but they annihilate the Laughlin state. So they are actually frustration-free Hamiltonians at specific fillings or below specific fillings. And for example, we know that the Laughlin state has the form some psi 0, and psi 0 usually contains these Gaussian factors and so on. And the main important property of the Laughlin state is that as two particles approach each other, the wave function vanishes at some high power. For example, at 1/3, it would vanish at a third power. Now, if I act with this Hamiltonian on this state, what I would do is that I integrate by parts to move the derivatives to act on this factor. So if I act twice, I would kill two factors of this. But if this power is more than 2, then I still have a factor zi minus zj left. And when I do the delta function, and of course, this would be Vri minus Vrj. So when I do the delta function, I will find that this object vanishes. So this pseudopotential annihilates actually all Laughlin states. And if I take higher pseudopotentials, they only annihilate higher Laughlin states. For example, so the 1/3 state is annihilated by V1. The 1/5 state is annihilated by both V1 and V3, and so on. And of course, this sequence only have the odd powers because the even powers vanish by antisymmetry. So how do we make use of this argument to understand something about more general bands than the lambda level? If you look at this argument, you see that the main feature of the lowest lambda level that allowed us to write a state like this, which would be annihilated by these short-range interactions, is our ability to write the wave function by multiplying factors like this, zi minus zj. Another way to interpret this is that the wave function always have the wave function seen as a function of one of the particle coordinates always have a 0 at every other particle coordinate of first order due to a Pauli principle. But in the Laughlin state, we have a higher order 0, which means we attach to other particles vortices. So this ability to attach vortices is the crucial ability that allows us to construct Laughlin states. And one very important aspect of this ability to attach vortices is that when we multiply a wave function by zi minus zj, and if this wave function is in the lowest lambda level, after I do this, it remains in the lowest lambda level. And that's precisely the property that is captured by this condition. So this condition tells me that if I take a wave function in the band and I multiply it by this vortex function, x plus iy, it remains in the band. And as long as the band satisfies this property, I can construct Laughlin states. I can prove that these Laughlin states are exact ground states of short-range interactions. And this, although, so this led to a concept that has been called in this last paper vortexability. So we can build Laughlin states in a band that is vortexable, which means that we can attach vortices to the wave functions. We can attach vortices to the wave function without getting out of the band. So we can see that this condition is actually the definition of a vortexable band. Of course, phrased this way, vortexability is a conceptually different way or conceptually new way to look at the structure and to understand its physical implication. But the notion of vortexability also gives you something a bit more, because you can choose to define the vortex function not as the simplest possible choice, which is x plus iy, but you can choose different choices for the vortex function. So the vortex function is some general mapping from R2 to the complex numbers. And I mean, I will not go into these details, but in this last paper, they explained in detail what gives a valid vortex function. But as long as these conditions are satisfied, and these vortex functions can be very different, so they can be x plus 5 iy, but they can also have some nonlinear effects that deform the vortex in different dimensions, in different directions differently. But as long as the vortex function satisfies a certain set of conditions, all these arguments go through. Of course, the disadvantage of this more general structure is that it allows you to make the same statements about many body, but you don't have the corresponding structure in momentum space. So it's not very easy to detect them numerically if I just give you some numerical wave functions of the bands. So yeah, I think this is a good point to stop. So just let me summarize what I discussed today. So we started from this curious limit of the Bister-McDonald model, where we switched off some term that maybe at the beginning it didn't seem clearly justified why we did this, but we found that the resulting model has a lot of interesting properties. So first, it has an extra symmetry, the chiral symmetry. Second, it has perfectly flat bands at a discrete set of magic angles. And these flat bands seem to give some theoretical explanation why why these flat bands appear in the more realistic Bister-Serre-McDonald model. So instead of needing to tune an infinite number of parameters, we just need to tune one parameter. And third, it turns out that these flat bands have very interesting structure that contains some of the features of the lowest Landau level, but also some other aspects. For example, the Berry curvature can be very non-uniform, and we still have Landau level-like physics. And we found that this structure can be phrased in very different ways. So it can be equivalently phrased in terms of this quantum metric or quantum geometric tensor, or holomorphic structure in real space, or holomorphic structure in momentum space. And we found that the particular perspective of holomorphicity in real space is the one that is most useful in understanding how these bands will mimic the interacting physics of the lowest Landau level. So yeah, that's it for today, and thank you all for your attention. Yeah.
How does the dispersion depend on the ratio between the AA hopping and the AB tunneling?
So at the magic angle, so at the magic angle, yeah. When this ratio is 0, you get 0 dispersion, and you switch it on, you get some dispersion. Usually, at the beginning, it's very small, but then as you go around 0.6, 0.7, it starts to increase. But even around 1, you get a reasonably flat band, and that's the case at the first magic angle. I think that the magic angle, second and higher magic angles, things are more complicated. So as you go away from the chiral limit, dispersion grows more quickly.
The leading more linear in the ratio?
Okay. I think so, but I'm not entirely sure. So I mean, how does it go with the W0? Okay, I don't know. I don't know what the leading order is. I think no, it could be quadratic. I think as you deviate from the magic angle, it definitely goes linearly. But in W0, I think it's probably quadratic, not linear. But yeah, I knew it at some point, but I forgot.
Dispersion cubic in K.
Well, so the dispersion at K and away from K. So the dispersion is linear, but then even not in the chiral, like away from the chiral limit, there is a point at which the leading term in that dispersion vanishes, which so the linear piece vanishes. Then it will be probably cubic because of symmetries. But again, it's something that's easy to check, but I don't know the answer right away. Other questions? Yeah.
Does the vertex-ability condition give you constraints on wave functions in higher Landau levels?
In higher Landau levels. So it's kind of an ongoing research topic, how to define a notion of vertexability for higher Landau levels. So as I said, vertexability tells you that the band looks like lowest Landau level. So you can ask what definition or what concept tells you a band looks like higher Landau levels without being like what band looks like first Landau level. So one approach is to use this property to say that a band looks like the first Landau level if we can find a Parter band that looks like the zeroth Landau level, so that the both together are vertexable. So that would be a way to define vertexability for higher Landau levels. There are different ideas that are based on some generalizations of this relation, finding a way to generalize these relations. So the paper from Ji Wang and others. But I think the important question, of course, is what. So we know lowest Landau level is good for Laughlin states because of pseudo-potential arguments. We know based on experiment that higher Landau levels have some non-abelian states, but the energetics of why that happens is a bit less understood. So without understanding that, I mean, you can do generalization, but it's not clear what's the physical motivation for these. So yeah, so the vertexability is the nice thing. It has a physical motivation, which is that you can vertexable bands are the ones you can do pseudopotentials in.
All right. If there aren't more questions, let's thank Eslam again.